Hi there. I hope you're having a nice day so far. So, yesterday we talked about basic statistics that you knew from middle school and ninth grade. And today we're going to explore another option called standard deviation. So, first to think about why we need some other kind of measure here, take a look at these two box plots representing test scores. Perhaps it says test 1 and test 2. Now, some things that we might notice about these test scores is they have the exact same median. They have the exact same maximum and the exact same minimum. And they have the same upper quartile. So in fact, those upper quartiles, that upper 50%, is spread out between the same two values there. Now, there is a little bit of variation in the lower half of the data, right, depending on kind of how those scores are spread out. But just on this box plot alone, it's hard to tell, which test did better. Maybe we can tell test 2, there were 25% of kids or students in a higher range of scores from 9 to 12 than in test 1. But for all we know, not only could they have the same median, but they could actually have the same mean. So we need just another way to compare data. So that's where the idea of standard deviation comes in. So standard deviation is a measure of how spread out data is. So this is a little bit different than range because range tells us the entire spread from smallest to largest. But standard deviation really compares the data to the mean. So it's a measure of how spread out data is relative to the mean. So for instance, if we have a smaller standard deviation, that means that the data values tend to be close to the mean, whereas a larger standard deviation means that the data values tend to be more spread out. So standard deviation is not just a phrase, the values happen to be more spread out, but it's an actual mathematical calculation. So we're going to talk about how to calculate standard deviation. And this is actually standard deviation for a population. And we'll clarify that in the future here, but for right now, we'll just keep in mind that this is standard deviation for a whole population. And so in order to do that, we've got this delightful formula right here. It says the standard deviation is equal to the square root of the sum. That symbol right there means the sum of x minus x bar squared all divided by n. So there's a lot going on there. And so, some textbooks will give you this formula and just give you some information. So for instance, S is the standard deviation. Okay, that's the thing that we're calculating. Great. X is the value of a term. So when we see X, we're talking about the value of a specific term that appears in the data. That X bar is actually the mean. So we calculated mean yesterday. We add up all the values and we divide by the total number of values. And the N represents the number of data values. So again, you could just take this this formula and I could say good luck, but I'm not going to do that to you. We're going to practice just how we would actually calculate this and kind of take some steps to make this easier for ourselves. Think back to the quadratic formula where we could break it down into smaller pieces and it was a little bit easier to use. So, for example, I have some data values. I've got 5 data values. 6.9, 8.7, 7.6, 4.8, and 9.0. So I'm going to calculate the mean. Now we reviewed yesterday that the mean is adding all those values up and dividing by the total number of values. So if you took a moment to add those up, you would actually get 37. And there are 5 values. So 37 divided by 5 is 7.4. So we're going to make a little table here to help us through these calculations. So the first thing is I took all of those data values, those 5 data values, and they are in this column, the X column. So then what goes in the X bar column is our mean. So I'm just going to put 7.4, whoops, 7.4 in every row of this column. And then the third column, X minus X bar, so that's saying just take these first 2 values and subtract 7.4 from our values. So 6.9 minus 7.4, 8.7 minus 7.4, 7.6 minus 7.4. And you will get some negative values as you do this. So 8.7 minus 7.4, that's 1.3. And then 7.6 minus 7.4, that's 0.2. And then we have negative 2.6. And 9 minus 7.4, oops, is 1.6. So then this last column is exactly the same as the one before it, except for we're going to square those numbers. So what this does is it makes everything positive there. And the reason that we're squaring and making everything positive is that standard deviation, if we're talking about how spread out something is, we're kind of talking about a distance from the mean, and we measure distance in positive values. So if you were to take a moment to square those and very carefully, you would come up with this column here. You're welcome to pause and check this for yourself and try it out. 6.76 and 2.56. And so if we look at this formula, the sum of all of those squares, well, really is just taking all of these numbers and adding them up. So again, if you were to take a moment to pause and add those up, you would actually get 11.3. And so that 11.3 represents this sum, this entire statement in the numerator under the radical there. So 11.3 represents the sum of all of the squares of the difference between my values and my mean. So again, I'm thinking about how far are my values from my mean? Well, we have to actually measure that, and we did. And then n represents the number of data values. We have 5 data values. So I'm going to put n as 5. So if we were to simplify that, 11.3 divided by 5 is 2.26. Then if we were to take the square root of that, we get approximately 1.503. So our standard deviation is 1.503. So again, just to recap the steps that we took, we started by finding the mean, and then we noted how far each of our data values individually was from the mean itself. We measured, or we reported that distance, and then we squared those distances to make them positive, added them all up, and divided by the number of values. So you could kind of think of this as an average of its own, right? We're adding things up and dividing by the number of values, and then finally a square root there. So what does all this mean? What does the standard deviation say about this data? Well, the cool thing about the standard deviation is what it actually tells us is that approximately 68% of our data is within one standard deviation of the mean. So look at a little bit at what that means, but for right now, I'm just going to make note of that. Approximately 68% of data is within one standard deviation from the mean. So what that means is that if I have my mean, my little X bar, whatever it happens to be, if I add 1 standard deviation or I subtract 1 standard deviation, so that actual number, the standard deviation, I'm going to get 2 numbers. And within those 2 values, so a smaller number and a larger value, within that interval, about 68% of your data is going to be. So for our case, 7.4 was our mean, and so thinking about adding and subtracting, so adding 1.503 or subtracting 1.503, we end up with 8.903 and 5.897. And so this tells us, one, our standard deviation is 1.5. So depending on the actual context, that could be a large or a small number. But it tells us that a good majority of our data is within basically more or less 3 units from one another. So again, the larger a standard deviation is, the more spread out it is, and the smaller a standard deviation is, the less spread out it is. So example 2 is going to provide a little bit more context for us and just kind of think about what this all means. We're going to get example 2 started together, and then I'm going to have you work on it on your own and come back in to check. So we have the number of U.S. hurricane strikes by decade from 1851 to 2000. So the number of hurricanes that actually made landfall in the United States. And so what are the mean and the standard deviation for the data? So our goal is to figure out what is that standard deviation. So what I'm going to have you do is I'm going to have you pause and actually try to work this out. If you get stuck along the way, you can come back in and check. Otherwise, come back in and check and we will compare our standard deviation. Welcome back. So hopefully, if you went through that entire process, you got a standard deviation of 3.5176 approximately, with just a little bit of rounding there. So if you got your standard deviation correct there, congratulations, you made it through a lot of steps along the way. If it wasn't quite the same here, let's just double check a few things. So first of all, starting with our mean, of course, if we add up all of these values, there are 15 values, by the way, right? If we add up all those values, we get 264. And so dividing by 15, we get 17.6. So again, that goes in my little X bar column. I'm going to put 17.6 in all of these rows. So you would fill this entire column with 17.6. And then our second column is bound by that difference. So 19 minus 17.6 equals 1.4. 15 minus 17.6 equals negative 2.6. So I know this is a lot to do by hand, but it's going to give us that measure that we're looking for. So I've got 2.4, 4.4, 3.4, 0.4, 3.4 again, negative 4.6, 1.4, 6.4, negative 0.6, negative 3.6, negative 5.6, negative 2.6, and negative 3.6. So I've got all of my differences there. And then again, that fourth column we take just by squaring the number before it. So 1.96, 6.76, 19.36. Oh, I made a boo-boo. That was the next one, actually. Sorry. This one should be, the third value should be 5.76, then 19.36, then 11.36, 0.56, 0.16, 11.56 again, 21.16, 1.96, 40.96, 0.36, 12.96, 31.36, 6.76, and finally 12.96. So we're double checking 30 different values. So if there happened to be one mistake in there, again, that doesn't mean that you don't know what you're doing, right? It means you made a mistake. Even if you're feeling you're not quite sure what you're doing, this is the very first time that you've done this. And remember, nothing goes perfectly the first time. So one more step here. Now that we have verified all 15 of our squares there, we take the sum of that last column and hopefully we get 185.6. So that goes in the numerator, 185.6, because that number represents the sum of the squares of our differences. And then we have 15 values. So when we do that, I would do that all in one step using some parentheses in my calculator. I get 3.5176. So again, if I think about where my data is, my mean was 17.6. And if I'm adding 3.5176 or subtracting 3.5176, that's going to tell me that when I think about hurricanes in the United States over the course of several decades, I'm just going to do that subtraction, 0.824. That means that the majority of any decade, so any decade or any decade in the future, is fairly likely to have between 14 and 21 hurricanes. And now that seems kind of like a big spread, especially when we're thinking over 10 years, and that doesn't tell us how many hurricanes per year. But what it is it's an additional data point. It's an additional bit of information. So we're going to keep practicing standard deviation. You have a short assignment to practice that to get started on. But as we do this, keep in mind that we're moving towards applying this. So today may feel a little bit tedious, but we're building skills to be able to explore some bigger topics. So go ahead and get started on your practice assignment. Again, you're welcome to work with a classmate. Have a wonderful rest of your day.